Hi everybody, welcome back. In this video, we're going to take a look at the convergence properties of 4 different well-known optimizers to better understand the criteria for selecting an appropriate optimizer for a particular problem. As you know, for any given optimizer, the learning rate is a key parameter that can affect how well your model performs and must be carefully tuned to optimize performance. But one topic we haven't yet discussed is how to select an appropriate optimizer, and that's going to be the focus of this notebook. We've already discussed the theory behind each of the optimizers in this notebook, and we've seen some interesting animations for how they behave with a three-dimensional loss function, which can be easily visualized. But now we're going to train a simple model with each optimizer so we can compare the convergence properties of each in a more realistic setting. One thing we wanted to emphasize up front is that when comparing optimizers, we want to make sure to compare the convergence properties on the training data set as opposed to the validation data set, because the job of the optimizer is to perform well on the training data. Most of the coding aspects in this notebook represent material that we've already covered earlier in the course, so we're not going to spend too much time reviewing coding details, but we'll briefly walk through the notebook to get familiar with the structure, and then we'll focus our attention on discussing the results. As usual, we have a system configuration function, and then we're also setting up some training and dataset configuration parameters. In this particular notebook, we're going to be using the Fashion MNIST dataset, which is very similar to the MNIST handwritten digit dataset that we've used previously in the course. In fact, the dataset has the same number of training and test samples with the same size images representing 10 classes. Next, we're defining a function to load the MNIST Fashion dataset and also a data preprocessing function that we've previously used in prior notebooks. Here we're defining a function to visualize a few of the samples from the dataset, as you can see below. And then in this next section, we're calling the preprocessing function to preprocess the dataset prior to training. Next, we're defining a function for the LeNet 5 model architecture. And in the next section, we're going to define a function that's going to be used to compile and train the model for each of the 4 optimizers. And notice that the function requires the training and validation datasets as input, as well as an optimizer flag that indicates which optimizer we'd like to use. So after we set up the directory structure on the file system for saving checkpoint files, we're going to create the model, and then depending on the optimizer flag that was passed into the function, we'll compile the model with the appropriate optimizer. One thing we wanted to mention at this point is that for each optimizer, we're not going to specify a specific learning rate, but rather we'll be using the default learning rate for each, mainly to establish a baseline, and also since the default learning rate is usually a good place to start. It's also worth mentioning that RMS-Prompt and ADAM both have different learning rates that are an order of magnitude smaller than stochastic gradient descent, which is due to the design of the optimizer and also based on a lot of empirical data. So for this reason, it really wouldn't be appropriate to use the same learning rate for each optimizer, but rather start with the default learning rates for each and then possibly refine that for subsequent experiments. And then finally, further below, we're going to call the fit method to train the model, and this is going to return a results object, which we'll use to plot the results for each optimizer. So this is just a convenience function that we're going to use to train the model for 4 different optimizers. And again, this is all material that we've seen in previous notebooks. Then in the next 4 sections of this notebook, we've provided a reference for the update rule used by each optimizer as well as the API documentation. And in each of these sections, we're calling the train model function. So let's now skip ahead to the training plots and take a look at the results. As we mentioned earlier, when evaluating different optimizers, it's important to study the convergence behavior on the training dataset. And specifically, what we're looking for is an optimizer that converges fast and eventually achieves a low value for the training loss. In the plot below, the first thing to note is that stochastic gradient descent has the highest loss of the 4 optimizers, while the ADAM optimizer eventually achieves the lowest loss. Stochastic gradient descent with momentum, shown in blue, follows a very similar trend to the ADAM optimizer, but with a slightly higher loss value. And if you take a close look at the curves, you'll see that RMS-Prompt, shown in black, starts to converge faster than the other optimizers, but after about 15 epochs, the rate of convergence slows down considerably and flattens out. So based on these results, we can conclude that the Atom Optimizer is probably the best choice since it achieves the lowest loss and demonstrates the fastest convergence compared to the other optimizers. But it's worth mentioning that although Atom generally performs well under a wide range of conditions, it isn't necessarily the best choice for all problems, and you should at least experiment initially to see which optimizer looks the most promising for your particular problem. And then once you've selected an optimizer, additional tuning will often be required to achieve the best results on the validation dataset. Before we conclude this notebook, we wanted to mention a few things about the validation loss. As we've seen thus far in the course, validation loss is something we pay a lot of attention to when it comes to the iterative process of experimentation and model optimization. But in the context of selecting a particular optimizer, we should use the training loss as a guide since the job of the optimizer is to perform well on the training data. However, let's just take a look at the validation loss for each optimizer and talk about the results. Based on this plot, you might be tempted to conclude that stochastic gradient descent might be a good choice because we see that the other three optimizers start to diverge after about 10 or 15 epochs. But if you take a close look at the plot below, you'll see that the other three optimizers actually achieve a lower validation loss between 8 to 15 epochs, while the loss for stochastic gradient descent never quite reaches an equivalent value. So what this plot is emphasizing is that for the validation data, the other three optimizers converge much more quickly and achieve a lower validation loss compared to stochastic gradient descent. Although there is tangible information in this plot, as we just demonstrated, it's really secondary information in the context of selecting an optimizer, whereas the training plots give a better indication for which optimizer to use. That said, once an optimizer is selected, we must use the validation loss to properly tune various hyperparameters to achieve the best results. So that's all we wanted to cover in this video. Thanks so much, and we'll see you next time.